Hi guys, welcome to the clip. Uh, I hope that you saw the first clip about introducing these three distributions. Now let's complete to talk about the relationship between these distributions. You know, there's a lot of distributions, but um, we focus on these three distributions because there's a lot of live applications for those three, and especially for I think people who work with the quality control ideas. Uh, I think you know how we uh, get from one distribution to another to calculate the upper and lower control limits and so on. We're not going to talk about much about this stuff, but uh, I'm trying to make a light about why we need these three distributions and we need this relationship between those. Uh, I'm going to give you a simple ideas how we can say if a random variable is binomially disputed, so it's Poissonly disputed. I'm going to give you the uh, only the results, like a simple idea. If you have condition is met, so you can move from one distribution to another. But if you want guys to talk mathematically about how these ideas has been proved, we can talk about it. You can just suggest it in a comment, like some one of you guys want to see a clip about how we can prove these theorems, and we will talk about it. But most of them use the essential limit theorem and some mathematically equation solvings to move from one distribution to another. Now, let's say that I have an x follows a binomial distribution with two parameters n and p. Okay. Uh, Sorry, I should write it as like this. You get the idea, but I'm kind of bad of handwriting on this board, so I'm sorry if it's something not really clear, but I think you got the idea. Two parameters n and p. I have a variable that follows the binomial distribution. Then I can say it's Poissonly distributed if n, first condition, n is large to p is small, which p, these p. Talking about these parameters. If these two conditions are met, I can say this variable is follows the Poisson distribution with the parameter lambda, which equals n times p. And if I have x is binomially disputed with two parameters n and p, I can say that this x is normally disputed if n is large and p is approximately 0.5, like for example 0.4, 0.6, and so on. Then I can take lambda is np, sorry, n times p, and sigma n times p times q, uh, sigma square, sorry, and then I will have a normally disputed variable. The idea between about these two conditions that n times p, n times p, and n times p times q both should be greater or equals. Sorry, I don't think that you're seeing this in the screen, so I'll write them again. N times p should be greater than 5 n times P times Q, I mean 1 minus P should also be greater than or equal 5. And sorry. If I have X is, let's erase this stuff. If I have X around the variable follows a Poisson distribution, then I can say it's normally distributed with a lambda expectation and lambda as a variance, or square root of lambda is a standard deviation. If this condition is met, which is lambda should be large. So with this idea, you can move from one uh, variable to another. And I'm going to say it again, guys. If you want to say how these uh, ideas has been done, like these theorems, we can talk about them, just ask. But I'm not going to waste your time in this clip. I'm not going to make a very long clip to talk about these theorems, because I think most of you guys just want to know main stuff about distributions and how can we apply them. So that's why I haven't been talking about these uh, deep math uh, topics. Now, let's talk about some examples. I have X is a random, sorry, two normally, no, just one word. I have X is a normal distributed variable with mean equals 30 and standard deviation is 4. I want to find the probability that X is less than 40. Now let's talk about a small simple idea. Like, I have X is a normal distributed function. I have the density function. I can calculate it, but it's going to be sometimes like hard to calculate this probability using the equation that we have seen before in the previous slides. So there's a simple step we can do to transform this variable from a normal distribution variable to a standard normal distribution. We can use the score uh, idea. We can take this value. I want to calculate the probability of X less than 40. I'll take this 40 and I'll subtract the mean of it and divide it by 4 as the equation that I have seen previously in the other slides. Let's go to it. This is it. You see, I can use this equation and I will get a new value, new score. We can call it z-score, and it's going to be 2.5. If I want to calculate the probability of x, sorry, capital X, sorry, should be capital X, probability of x less than 40, it's the same that probability of z is less than 2.5, and it's going to be a really big probability, 0.99, like almost sure it's going to be less than 40. How do we calculate this? uh, we're going to do it by software. We're going to use our software. I don't think much of you guys want to uh, try to calculate it by hand, but I thought before, if you want some clips to solve some examples by hand, we can do that. I'll make a clip for you guys. Another example about binomial distribution. X follows the binomial distribution. X represents the numbers of heads, the number of heads occurring by throwing a fair coin 3 times. So I have an experiment which is I'm throwing a fair coin 3 times, and I want to calculate some probabilities about the number of heads. So I denote x is the number of heads occurring by throwing a fair coin 3 times. Now I want to find the probability of x equals 2, while this p equals 0.5. Like, what is the probability of getting a head by throwing a fair coin 1 time? It's going to be 0.5. Because I have a fair coin, I'm not going to uh, like, for example, cheat on this coin, like, for example, uh, move it around or something, or so on. I have a fair coin. So uh, first thing, we should calculate sample space. Like, I'm throwing a fair coin 3 times, how many results that I can get? I can get head, 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 tail, head, tail, head, tail, head, head, so on to tail, 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 tail. It's supposed to be 8 sets. I can calculate this number of results I can get by taking this equation S results on power trials. How many results I can get? Head and tails, so it's 2. Trials, how many trials? I'm throwing the coin 3 times, so power 3, it's going to be 8. You may say, like, why I need this equation? I can write these sets and I don't need to use it. Sometimes you may throw 5 coins, 6 coins, and so on. So it's going to be hard to write all the sets and calculate them. So this is a fast way. Uh, Now I'm going to calculate the probability of x equals 2. We have seen the equation before. This one, you see. I'm just going to get this equation and put it here and calculate the probability of getting 2. This is a combination 2 of 3, so I'm using it as a factorial. 3 factorial 3, factorial 3 divided by factorial 2 by factorial 1. This one should be 1. If you completed this equation, it's going to be 3 divided by 8. Like, I think it's going to be, sorry for bad handwriting, 0.375. Now let's go to work a little bit with R. Sorry guys, I'm kind of sick. So uh, most of you guys should be a little bit comfortable with working with R Studios. I'm not going to talk about how we can use R, how can we configure it, install it, and so on. I think uh, you know you know how to work with it. So I'm just going to talk about a little bit functions about distributions. Like, let's talk about normal and binomial distribution. R gives a lot of functions about a lot of distributions, but for our example, we'll talk about normal and binomial. For each distribution, you may see 3 to 4 to 5 functions for each distribution. For example, for binomial distribution, you have a dbinom to calculate the probability mass function, pbinom for cumulative probability function, qbinom about quantiles. We may talk about it later. rbinom to generate random variables, random values, which are binomially disputed. Um, and for normal distribution, there is a deep norm for density function, p norm, q norm, r norm, and so on, as a previous one. So let's talk about the examples that we have talked about before. So let's return to this one. Our first example was I have a variable x is uh, normal disputed with mean 30 and standard deviation 4, and I want to calculate the probability of x is less than 40. Let's go to R. I'm using here the p norm. Why? Because I want to calculate the probability of x is less than 40. P norm 40, 30 and 4. First value is the value that I want to find the probability for it, which is less. We can talk about greater and less and so on in other clips if you want to. For our example, I'm going to put three parameters: 40, our value, and 30 is the mean, 4 is the standard deviation. If I run this command, we're going to get 0.99, the same as our result. Uh, if you want guys to see your point, like where is it on the uh, normal distribution curve, first let's plot it. This is how the normal distribution look like. uh, I'm using some simple commands about plotting and about graphics because this clip is not focusing about how to use like interactive and modern graphics, so I'm using some simple ones. You can see that our value, which is 40, if I transform it to a z-score, it was 2.5. This is our value, and I'm calculating this whole area, so it should be a big probability, as we have get 0.99. The second example was I have uh, an x random variable which represents the numbers of heads that I'm going to get by flipping three coins. So I put the second parameter is 3, the number of trials, and 0.5 is p, and 2 is the probability that I want to, the value that I want to calculate the probability of occurring it. How many heads? 2. So I was calculating the probability of x equals 2, and this is the command to calculate this probability. If I run it, it's 0.375 at the same result that I have get before. Let's talk about this example. R norm 105 0.5. This is a function which is going to generate 100 points with mean 5 and standard deviation 0.5, because this value is going to be for a variable which is normally disputed. You see, now I get 100 values. The second one is the same idea, to generate random numbers, but this one for a discrete random variable which is binomially disputed, 100 points values with 3 trials, 0.5. So as you've seen, like it's like the example of throwing a fair coin 3 times. Like first time the x was 2, then 3, then 0, no heads, 3 heads, 3 heads, 2 heads, 1 heads, and so on. Now let's talk a little bit about the approximations that we have talked about, the relationship between these three distributions. I want to run this command and it draw for me the normal distribution. The second one is going to, it's a simple example to draw the Poisson distribution, and third one is for binomial distribution. You may see some cracks, breaks here because it's a uh, discrete probability distribution, and I'm plotting it as continuous. So it's kind of simple to see these breaks. My example here will show you how a variable like x is binomially disputed will be Poissonly disputed. Let's see here. This statement is for the probability mass function for binomial distribution for 0 to 15 values with 15 trials and 0.5 p. So this density function or for discrete random discrete probability function, it's probability mass function we call it. We should know that this probability mass function is for binomial, but if I try to run this command to see the shape of it, it's going to be normal. Why? Because I have n is large, kind of large, and 0.5 is the p. It's approximately 5. You know, in this example, it's the same as 0.5. We've talked before that if I have a x is a binomial distribution with n large and p is approximately 0.5, this variable is going to be normally disputed, right? So if I run this command, you will see the shape of a normal distribution. Why? Because the two conditions are met, which are the n times b and n times b times 1 minus b. Both are greater or equals 5. And you can see here 50 times 0.5 is going to be 25. It's of course greater than 5. The second command will show you that the binomial distribution function, if I plot it, will be Poissonly because this time the n is large and p it's kind of small, as you see here 0.15. So it should be a probability mass function, a density function, as we're talking like for plotting, for the idea, for the sake of idea. Um, it should be binomial distribution, but if I run it, it's going to be Poisson. We have seen the shape of Poisson before. You see, it's kind of the same because these two conditions are met. N is large, P is small. The third shape will show you that the X follows a Poisson distribution will be uh, normally disputed. If the lambda is large and the same, I wrote the command, this command as the same of these previous ones. So the same idea. I have lambda as large. If I run this command, I will see a normal distribution approximation of Poisson. So the relationships that we have talked about are right. You can try to play a little bit with the R studio R commands to see what shapes that you'll get if you change the parameters and so on. Um, I thought you guys know much or at least some simple ideas about the R Studio and R how to write R commands. So you should be familiar with these commands. If you guys don't understand what is going on with these commands, we can talk a little bit about simple commands in R. If you have any question, if you have any idea you want to talk uh, about applying these ideas or as I have seen before, sorry, as I have said before, um, to talk about these theorems and proof, we can talk about it. Just comment on these uh, clips, and we'll do a clip for you about the things that you are interested in. So the clip is finished. I hope you guys get the most of it, and happy learning. Please subscribe for our channel, and bye bye.